Welcome to United Astronomy Clubs of New Jersey. Thank you all for joining us here in Jenny Jump State Park in Hope, New Jersey. And thank you everyone who's also joining us online. Because that's right, we do live stream these talks to both YouTube and Twitch. So if you're ever not happening to be here on a Saturday night, don't know why, but looking for something interesting to do feel free to check out our live stream. Because I see a number of people filing down, and I want to give them a little bit of time to get settled down, find a good spot to see the presentation behind me. Couple things. I do encourage everyone, check out our website, uacnj.org. It's where you're going to find a list of not only our upcoming and past talks, which you can check out. We have links for the past talks up there too, because we do keep them around. So never fear if you are like, man, I wish I was around for the Fermi Paradox talk. Don't worry, you can still see it on our YouTube. And you can look at what we have coming up as well. It also has a list of all our member clubs, because we are a club made up of other clubs. And the easiest way to get into astronomy is, that's right, looking up your local club. And just for ease of access, I know some of you have come from quite a distance, an hour or more away, so those are going to be excellent resources for you. You can also check us out on our social media. Follow us there. We put out updates on what talk we're doing that week and any other fun special events we might be doing, such as usually the last Saturday talk we have in October. Since it's so close to Halloween, we encourage everyone to come in costume, because yay, Halloween, spooky season. So if check us out online, like I said, hit those follow free buttons. Now that it looks like we've kind of settled down out here, we have the safety briefing. It is inescapable, and for the people who will inevitably sneak in during the presentation, I will give it at the end too. If you need to use the restroom, that is the porta potty. It is in back to my left, your right. It is big, it is blue, it is illuminated by a red light for ease of finding in the dark. Because that is right, we are in a state park, and it does in fact get very dark, despite light pollution's best efforts otherwise. So when we're walking around, if we need flashlights or whatnot to navigate the ground, do try and keep those lights earth pointed. We don't want to accidentally blind anyone, such as myself, doing sick tricks with your 100,000 lumen monstrosities you bought off of Amazon. I had absolutely no night vision that night, so I appreciate it if we keep those lights towards the ground. That being said, when we go to leave in our cars, we are using our headlights because we do not like getting run over. No one needs those medical bills, so let's keep the record of 0 people being run over going. So, with that, you're not here to listen to me blabber on. You actually want to listen to the talk. I will say we do have a question and answer session at the end, so we'll keep going through he'll give the talk, and at the end we'll go through the question and answer session, and I'll go through the rules of that then. But for now, you are here to listen to, and I'm just really sorry, Chirag?
Yeah, Chirag Skolar.
Okay, I wasn't sure the accent on your last name, too. But Chirag is a computational plasma physicist working at New Jersey Institute of Technology. He got his bachelor's degree in mechanical engineering at Boston University and his PhD in aerospace engineering at Virginia Tech. He is interested in all things plasma physics, and with a special focus on plasma material interactions related to renewable energy, nuclear fusion devices, plasma turbulence development in Earth's ionosphere, and improving remote sensing capabilities of non-Maxwellian plasmas, which is way beyond my educational pay grade of some college. So with that, he's here to talk to us about the problem of space trash.
Thank you very much for the wonderful introduction. The title of the talk I have for you today is Waste of Space, the Problem of Space Trash. It's hard to see, but by a show of hands, how many people have seen the movie Gravity? Okay, good. A decent chunk, decent chunk. So those of you who have might already have a general idea of what it is that I will be talking about. I'm going to start out with a little bit of history of all of this stuff and our efforts in space travel. Then I'll talk about some of the really cool cutting edge research that we're doing that yeah, I'm going to a conference in a few weeks that we're all going to be fighting over like who's got the right science and stuff. So this will be really fun and really neat. So the first thing is that's right. Okay. I wanted to give a brief history of space travel and everything that we've done as a society on how to build up our space infrastructure. So I've got a bunch of stuff on the timeline. I'm not going to go through every single bit, but the first event that I do want to point out is June 20th, 1944. Right there. So that's the first human-made object ever launched into space. It was a Nazi V-2 rocket that they were using during development during World War II, and they wanted to do a bunch of terrible things with it, and thankfully they lost, but that was the first human-made object launched into space. A few years later, a lot of that rocketry knowledge went over to the United States and the Soviet Union, and we had one of the most important dates in space history. October 4th, 1957, Sputnik 1 becomes the first human-made satellite to make its way into space. And then shortly after that, a whole host of things happened as the space race began during the Cold War. A few other key points here. You had Yuri Gagarin, first human in space. We have Valentina Tereshkova, the first woman in space. We have over here on July 10th, 1962, the Telstar 1 launched. And that's a really useful satellite for us to know because that's a weather satellite. And sorry, Telstar 1 is down there. That's the bottom right. That's the first communication satellite, and it's the first commercial satellite. So so many things that we use now, radio, TV, phones, the internet, so much of it gets beamed up to satellites for us to communicate with each other, to easily just, I'm on my phone and I can talk to somebody on the other side of the world really easily. But was not something that we were able to do at that period of time until we had all this nice satellite technology. And then in 1960, the Teros launched, and that was the first weather satellite. So all of our beautiful understanding of weather, where now it's kind of commonplace that you just open the news and you see, oh, the hurricane's over here and it's moving over there, and this tracking, that didn't exist until this period of time. So we have this wonderful, beautiful infrastructure that started out with some of these satellites that are being launched. And of course, we got Neil Armstrong taking the first steps on the moon. Wonderful advancements we've made as a society. Then we decided, okay, let's keep pushing past the moon. Let's go check out other places. We've checked out Venus, Voyager 1 and Voyager 2 launched, doing flybys of all the outer planets and some of their moons. February 22nd, 1978, another important point in our story, the first GPS satellite, the Navstar 1, was launched. I'm sure many of us today use GPS to get to where we are, and if it wasn't for this satellite and all of the ones that came after it, we wouldn't have the GPS cluster to be able to know exactly where we are, find where we're going. And now there's instances where farmers are using GPS to have automated tractors to help improve and mechanize our agriculture. So there's all sorts of really important uses of GPS infrastructure that comes from all the satellites that built there. More orbiters around Jupiter, Mars rover, Saturn, building the Hubble Space Telescope that were all really, really revolutionized our understanding of the universe. First part of the International Space Station. Then we even went and returned an asteroid sample, went around Mercury. Voyager leaves leaves our heliosphere into interstellar space, becoming the furthest human-made object ever. We have landed on a comet. We have the Parker Solar Probe that becomes the closest spacecraft ever to the sun, fastest human-made object ever. We've done really cool things in the names of science and trying to understand and explore the world around us. There's the James Webb Space Telescope that is going to do absolute amazing wonders that I'm sure has already been talked about on many talks at this observatory. But some key points that I do want to make that are going to be important for this talk is some of the developments that happened in 2015, for example, was the first successful landing of the Falcon 9 rocket. That's this one over here. I'm sure we've all seen images like this many, many times over now. This is 10 years ago now. It's crazy to think how far we've come, and that's really increased the amount of our ability to enter space and do all sorts of really cool stuff in space. And then next to that, I've got this GIF over here of a set of Starlink satellites being launched. Those were the first 60 Starlink satellites. There's 7,000 plus of them in orbit. That's 60 of them being launched in one go. And then they're all going to have little thrusters to bring them to their proper orbits later on. And the last historical point that I want to mention is on September 16, 2021, the Inspiration 4 launched, which was the first space flight of private citizens by a private company. So we're now getting to the point in using space that it's no longer like nation states that are the only ones that really are the only ball game in town. There's private companies that have the funds and the will and the means to get private people into space and like a space tourism kind of deal. So all this to say that we've done a lot of really, really cool stuff in terms of science, in terms of technology, in terms of engineering. And I think it's safe to say we've become a pretty good spacefaring civilization. We're not like a Star Trek kind of vibe yet, but we're doing a lot, and we're really building up our space infrastructure with more and more launches each year. As I've gone through some of the things here, we've built our space infrastructure over about 70 years. We've done communication satellites. We've got GPS, satellite imagery, any cool thing we see on Google Earth, or if we want to observe a spot remotely that's hard for humans to get to, we have the ability to do that. Science applications, there's so many science applications, I can't even name them all, but whether we're looking down on the Earth, whether we're looking in the space environment, whether we're looking up at the cosmos and the universe beyond for all sorts of cool things to learn more about the universe in which we live. And then there's weather observations, all the great stuff that we get in weather just on our phones we have, and this is all important because we built a space infrastructure to do this over 70 years. And you can see on the right here, I've got a plot of the orbital launches over the years. Early on, obviously, we were learning how to do space launches, so it ramped up. We stayed between 100 and 150 for a few decades. We went down a little bit into 2000s, and now we're ramping really way back up. And that ramp is really, in recent years, due to private corporations. A lot of that is due to SpaceX and the Falcon 9, which has allowed us to have so many space launches. Now, this is really, really cool stuff, and to me, this is a testament of like human ingenuity and how we're able to, we're on this little rock and make this beautiful infrastructure that we all use today. We don't even realize that we use it in our everyday lives. But humans are also really good at something else, and that is leaving a lot of our stuff around. This is all stuff on our planet right now. Your classic like turtle in a fish net and a bunch of trash on the beach. This one over here is a lot of our recycling in the West we think is actually getting recycled, makes its way over to more disadvantaged countries. These are workers in Indonesia burning plastic that we thought was getting recycled. On the top right is it's a plastic bag at the bottom of the Marianas Trench, the deepest part in our oceans. And the bottom right is a bunch of ocean currents called gyres that make it such that particles of debris that that make their way into the oceans kind of circulate into specific patches, like with the Great Pacific Garbage Patch. So I'm being like intentionally provocative here. The space is not quite like this, but it is kind of shows what we do to some of the environments in which we live, and if we don't do anything to be good stewards of where we are and foster a nice, sustainable space environment, we're not really going to be able to continue using space in a meaningful way. The nice thing, I guess we want to call it nice in some regard, is that the downsides of this is that it primarily only affects us. The downsides of this pollution is, we affect the beautiful other living things that we coexist on this planet with. But in space, the only ones that we're really affecting is us, because if we make our infrastructure difficult and untenable, then that's us that's really losing out here. So Yeah, this is a debris map of all the things that we have detected and know that exist in space right now as of August 2024. And only a very small fraction of these are actually satellites that are being used to do all sorts of really neat things. The majority of these are just other objects floating around, orbiting the planet. Most of these objects are in low Earth orbit. We can see that there's a lot of objects centered around the Earth, and it makes sense that everything's in low Earth orbit. It's easiest to get there. If we care about communicating on Earth or detecting things on Earth, and we want to make sure we're pretty close to it. So low Earth orbit is where the most stuff is. But then there's a secondary ring, and that's going to be more like a geosynchronous orbit, and that's where a lot of our GPS satellites live. Geosynchronous orbit is an orbit that rotates with the planet. So whereas most satellites, you'll just see them zooming by, you might even see a few tonight, a geosynchronous satellite is over there, and then in an hour later I point and it's still over there, right? So that's what makes it really useful for position keeping for GPS. Now, we don't need to worry too much at the moment in the sense that space is really big. I'm not talking about like, universe vast, unfathomable big, but just even the space around our planet is big. If we were to actually plot these dots to scale, you wouldn't see anything because the dots, these objects are so tiny compared to the Earth that you wouldn't see anything of what's going on. It would be like, oh, there's no problem. But it is something that we do need to take into account and consider, especially considering the amount of debris that we see increases yearly. So what I have on the bottom right here is a plot, and a lot of these plots I have are from the ESA, the European Space Agency Debris Report. It's a very fantastic report, gives all sorts of really interesting information, and they've beautifully disaggregated the data in terms of the orbits. And I'm not going to go into detail over all the orbits, but the clear orbit that we want is to look at LEO, low Earth orbit. That's this bottom section right here, and you can clearly see that over time the amount of objects in that orbit has increased. Now, where are all these objects coming from? In the plot that I showed earlier, the orbital launches is on the order of hundreds per year. And if you added all those together, you get a total of 7,016 objects. Well, on this plot, we see that there's 40,000 plus objects observed, but these are only the ones observed. We have reason to believe, based on implications of impacts from satellites that we have that have returned to Earth, and some other simulation models, we have reasons to believe that there's probably about 54,000 objects greater than 10 centimeters, 1.2 million objects between 1 to 10 centimeters, and 130 million objects between a millimeter to a centimeter. So how do we square this difference between the 7,000 launches and hundreds of millions of stuff up in space? That's part of it. One part is a lot of these objects are multiple objects that are shooting in orbit at the same time. Example, this is the same exact SpaceX GIF that I showed earlier. That's 60 things from one orbit launch, right? So that's part of it. And we can see on the right is payload launch traffic into, it's showing that it's going into LEO, low Earth orbit. So this is disaggregated by the type of entity that launched this. So we can clearly see in recent years, commercial entities have increased a lot, and most of this is Starlink. So the other things are satellites that stopped working. You could have parts that broke off of satellites. You could have rocket remnants. Now, for example, in this GIF, you have a rocket that is launching this set of Starlink satellites, so it's jettisoning them off into wherever their orbit is. But the rocket still has to go somewhere, right? This rocket might have made its way back down to Earth safely, but oftentimes the rocket says, okay, I sent it off, and now I'm just going to float here until I go away somewhere. So sometimes you have rocket remnants or things like that. You get chips of paint or leftover propellant. There's all sorts of shaking and motions that happen as you go through the atmosphere and you're tumbling and trying to understand how to detumble. So there's all sorts of things that cause little tiny bits of stuff to get loose. And the question becomes, okay, we have all this stuff, but why is this a problem? The reason this is an issue is because these objects move very, very fast, and I mean like incredibly fast. So on the top right, I've got a plot that I think I assumed like a simple circular orbit. If you in miles per hour in low Earth orbit, so anything to the left of that blue dashed line, uh, everything is like between 15,000 to 17,000 miles per hour. That's pretty fast. And even once you get to geosynchronous orbit, you get down to maybe 7,000 miles per hour. That's still really, really fast. And even if you have a tiny, tiny little thing, if it's moving at 15,000 miles per hour and it hits something, that's going to cause a lot of damage. So as an example, I've got on the bottom left, we got a 1/4 inch hole in the Space Shuttle Endeavour's radiator. In the middle, we have from the cause of a 0.2 millimeter speck of paint. 0.2 is a tiny little chip of paint. Hit the Challenger window at such speeds that you got this really large looking impact crater on the window, right? And this is for like like a space shuttle grade window. This is not just like your regular old car windshield. And on the bottom right, I have an image of a hole in in an arm that they use in the ISS to do some sort of neat space repairs. And you can see that these were all fine in that obviously we don't want anything like this to happen, but the things that it impacted weren't super vital. But suppose there was an astronaut doing a spacewalk during this ISS impact, right? That could have been something that could have been a huge tragedy that would be awful, and we really want to make sure that something like that doesn't happen. And now these are only for like really small pieces of debris. Now there's pieces of debris that are much larger out there, and by pieces of debris that are much larger, I mean like suppose you have a satellite that doesn't work anymore, and now it's just sitting there, orbiting the planet. There's no real way for you to do any sort of things to get it out of the orbit. So what might happen? Well, what'll happen is what I have here is going to be a video of the first major debris causing accidental collision, and the accidental part is important, and I'll explain later. But we have on the right here the Iridium 33 satellite. This is a communication satellite. This was an active communication satellite. At the time, I don't know what it was doing, but it was being actively used for communications. And then, where do we see? Over here in the red, or whatever color that is, this is a Cosmos satellite. This was an inactive satellite and wasn't being used for anything. And what we'll see is that the two of them are just going to make their way towards each other. And in an instant, you went from a functioning satellite to a satellite in a bunch of little pieces traveling, but those pieces continue to travel along their orbital path generally, and they're going to go back around. They're going to cross again another time. There's going to be some chance for some of these to have further collisions, and then this sort of cycle keeps continuing. So we can clearly see just from one terrible catastrophic event, we've made so many little pieces that could cause huge problems later on. And these are the little pieces that might have caused some of the other issues in the smaller holes and stuff I showed in the previous slide. So now if we take this idea and expand it further, the number of particles that were generated during that collision at that time, they accounted for 10% of all the tracked objects, which is a huge amount. So that one event created a huge amount of additional space debris. And some of these objects will remain in orbit until 2100 or even later. This bottom left plot here shows the decay of some of those debris pieces as a percentage. And what's also really useful to understand is that they don't stay exactly in their orbital plane. That would be nice. I mean, it would suck for if you had a satellite in that orbital plane, but it would be nice if at least they stayed in that orbital plane. Over the course of a year, we see on this plot, on these set of plots, In 7 days, they're kind of along their orbital planes. In 30 days, they continue drifting. 6 months continue drifting. By a year, they've taken up a really large amount of all the different orbital planes in that general uh, altitude range. And you can clearly see just from one catastrophic event, you go from a localized amount of debris to debris that might span over the entire range of the planet. So if we look at this from a historical perspective, and we look at the major collision events that are seen in our history of observing all of this stuff, this is the same exact plot that I had showed earlier of looking at the debris that was disaggregated by orbit, but now we've disaggregated it by the type of debris that we have here. So there are a few key timeline events that I wanted to show here. So in 2007, in 2007, there was a Chinese ASAT test. ASAT stands for, you might not be able to see it on the bottom left here, but ASAT stands for anti-satellite weapon, right? And that's why I said before the other crash was the first accidental crash, right? Because people have deliberately caused a crash before to see if they could do something to, get rid of some sort of satellite. If some country's military doesn't care about some other country's military satellite, right? So you can see this Chinese anti-satellite test. This color here, pardon me, I am a little bit colorblind, so I don't know my colors very well. I think this is a light blue, but it's whatever it is. You see this value goes from this part to this, so there's a huge jump in the number of debris particles of payload fragmentation debris. That's the specific value that we're looking at here. Then we go a little bit further in time. We've got the Cosmos Iridium collision. That's the video that I just played for you. Then there's like slow increase over time, and that kind of is just like a natural thing that we should expect to happen. And then over here, if I can find my mouse again, over here we have a Russian anti-satellite test, which also increased the amount of payload fragmentation debris. We have above it a propellant tank exploded, increasing our rocket fragmentation debris. And at the top, I wanted to point out that we also have all these additional, starting from around here going forward, you have these additional unidentified objects. And that is mainly, over time, we've also just improved our detection methods. So a lot of these unidentified objects probably existed beforehand, and if we had measured them before, they'll probably be in one of these other bins. But we measured them and we're like, oh, we don't know where they come from, so we just put them in unidentified. What this tells us is that the number of debris particles are increasing over time, and there's been a lot of collisions. And the last bit I want to point out here is there's the Starlink satellites. You can see this bottom color here is an actual payload. These are actual functioning satellites that we're using that are doing all sorts of cool stuff. These are the good ones that we want to keep, but we also need to note that there are a lot more of them because of the Starlink satellites. And I point out China and Russia here, but they're not the only bad actors. You just can't see it in these plots here. The United States and India have also demonstrated capabilities for anti-satellite weaponry. And specifically what I want to point out with the Russian anti-satellite test is it's very important for us to be aware as a society to not do this stuff, because in the 2021 Russian satellite test, they exploded whatever they hit, and that debris cloud went within the path of the International Space Station, and it was dangerous enough that they told the astronauts, hey, go sit in your escape pods for a few hours while it does a few passes to make sure everything's okay, because their escape pods have additional shielding. So this is certainly things that we need to take care of and understand, especially as we have all these additional objects. Now, the trend that we can clearly see is that the number of objects is increasing, and at a faster rate than what we had before. Part of it is because we measured more. They were probably already there to begin with. But part of it is we are putting more stuff up there, so we should expect that number to increase as well. Now, as we have this increase, I do want to kind of make an analogy towards another thing that we've heard for a very long time that's been increasing, that we need to do something to stop. So like with climate change and we have global temperature increase, there is, in a sense, a point of no return with our satellite debris. To give an example, consider this. If you have one piece of debris traveling through space, it goes and it hits a satellite. Satellite breaks off into three pieces. Now you have three pieces of debris. Maybe those three pieces of debris each hit a satellite. That satellite breaks up into another three pieces each. You've got 9 pieces of debris, etc., etc. I'm sure you can see where I'm going with this. So you get this chain reaction sort of idea, and this was first posited in a paper by Kessler and Pillay in 1978, where the basic idea is if you have enough density of objects, just the sheer number of objects that you're going to have in space is going to increase due to the additional collisions, and it'll lead to kind of an impassable layer of debris. This was kind of a field that was originally done for, like Saturn's rings, for example, is a very similar sort of effect. But now this is about our planet with the stuff that we're putting up there. And the important thing is that maybe it'll result in an impassable layer of debris. So if there's too much stuff in an orbit that you care about, maybe we can't use that orbit anymore. Maybe we can't even shoot through that orbit anymore without worry of it breaking whatever it is we're shooting through it. So this is a very important thing that we need to keep in mind in terms of our near-Earth space environment and make sure that we're fostering it very nicely. And this is a very aptly named Kessler syndrome, named after Donald Kessler, who was the man that posited the idea. So, in a sense, we're kind of already there. We're already having unstable orbits. What I have here is a plot where our x-axis is altitude and our y-axis is our spatial density. And there's a region between maybe 600 to 1600 kilometers where we're already in a position where, where we are unstable, where if we don't do anything right now, this will just continue to keep growing, and then eventually, we may not be able to have any more nice space infrastructure and do any sort of space operations. Don't panic, because this is a slow process. But panic a little, because we've known about climate change since the late 1800s, and we're still talking about it today and trying to get some sort of action done today. So ideally, we can talk a little bit more about it now to maybe get some sort of really cool, interesting work done to make sure that we can continue having really great space operations in the future. So in that line, what we have here is if the number of objects and collisions will continue to increase even if there's no more launches. So on the left is the number of objects in low Earth orbit. On the right is the number of cumulative catastrophic collisions. And the bottom lines are if we decided right now we're done with space. We don't want to do anything with space anymore, and we're just going to leave everything there as it is. You can see it's slow, but it's growing, right? But we're not done with space. As I've shown, we are continually increasing our launches and doing all sorts of really interesting stuff. But if we continue in the path that we're going without doing any sort of mitigation or getting rid of stuff, we can clearly see that the number of objects is going to increase, the number of catastrophic collisions are going to increase, and perhaps not in our lifetimes, but maybe either in our children's lifetimes or their children's lifetimes. Maybe it's going to really start becoming a problem that we need to actually do something about. The key thing to note here is that the reason that this number is continuing to increase, even if we don't add anything else up into space right now, is because the additional objects are being added at a rate faster than it will take for them to naturally decay out of Earth's orbit. So what do I mean by orbital decay? We tend to want to think of space as up there and there's nothing there, but really space is not a vacuum. There is stuff up there. There's a lot less stuff up there, but there is stuff up there. On the right, I have a plot from from an empirical model called EMSIS. We use it very often in our work to get an understanding of the neutral density as functions of all sorts of things. But the basic idea is our y-axis is altitude and our x-axis is the neutral number density. So at really low altitudes, we have a lot of stuff. That makes sense. We can feel it right now if we do this, right? As we get higher in altitudes, there's a lot less stuff. And even though there's a lot less stuff, that stuff is enough to cause orbital decay. Uh, the satellites up there, or whatever object up there, is going to be moving along, and some of the particles are going to continue hitting it. It's going to slowly lose some of its momentum until eventually it will decay out and re-enter and land on the planet. So any satellite that is actively wanting to stay over there has some sort of thruster on it to give it just a little push every now and then to maintain its orbit, because otherwise it's just going to come down. What I have in this middle table here is kind of an approximate example. There's a lot of other factors that will change the numbers slightly, but this gives you a general ballpark idea, right? If you're at an altitude of 100 kilometers, you're hitting the ground in 2 hours. But at 200 kilometers, it's going to take you a week, 500, 2 years, 600, 20 years. I'm going to 800, it's going to take you 200 years before you come back to the planet. So these are kind of things that engineers keep in mind when they're designing their space missions, and things that we need to keep in mind when we're looking at debris that are existing in our near-Earth space environment to see if, how many of them might re-enter, how many of them might stick around for a while. So this bottom left plot over here is a plot of the number of debris particles, or rather just objects in general, that have re-entered, not including human spaceflight re-entry. And you can see in recent years there's been an uptick, which is good. In the sense of there's less stuff up there. There's some more stuff down here where it lands. That's a different environmental problem for a different talk. The last point I want to make on this slide is we need to be especially careful about debris orbiting the moon right now. The moon doesn't have as much stuff around it. It's not a huge issue, but the moon has like no atmosphere, and we do. So that's like some sort of check that we have that's keeping everything kind of nice for us. So as we want to build moon bases and all these other infrastructures on the moon, we have to keep this into account, because then we might lose out on some nice space infrastructure on the moon too. So we have all these ideas of how these debris particles are made. We have an understanding that sometimes they decay. And what's nice is there are guidelines that exist to foster a really nice, sustainable space environment. They're set by the Interagency Space Debris Coordination Committee, or the IADC. It's basically a bunch of country space agencies came together and said, hey, we should figure out something to do to make sure that we can all keep using space. And some of these are kind of very obvious ones that make sense, but they're things that we need to actively consider when it comes to the engineering of all future space missions. Limit debris during normal operations, avoid explosive breakups, make sure that, after your satellite's done being used, make sure any potential energy that you had stored up in there somehow gets used up, so that there's no like catastrophic collision or explosion that happens later on. If you're in a geosynchronous orbit, move to a graveyard orbit that you can sit for 100+ years, so that we don't need to worry about that impacting any really important geosynchronous satellites. If you're in a LEO orbit, either do a direct reentry, tell your satellite, okay, you're done, it's time to come home now, and send it on a trajectory back down to the planet, or put it on an orbit that we know is going to decay within 25 years. What else we got? Oh yeah, I'll make sure that wherever it lands, it doesn't hit people or things that people care about. That's always very important. 10 to the -4 chance. You want to design your satellite mission to minimize the chance of accidental collision with known objects, right? If you're designing your mission and oh, there's like an object, really big object right here, to make sure your satellite's not there when it's there, right? It's things that make sense, but things that need to be thought of, because if you don't think about it and you're just like, I just want to make the satellite go up at my orbit, if you're not thinking about it properly, then bad things might be happening. You can perform active avoidance measures if you need to. If you detect that there's a satellite or some other object coming in your way, you could use a thrusters to slightly get out of the way and move back, or slightly change your trajectory to make it so that everything is safe. And these are all really great ideas. But sadly, the IADC is not a regulatory body. It's a guideline body, which is great, but it doesn't have any teeth. It doesn't have actually a way to impose penalties or anything to make it so that people are actually using space in a proper, safe, and sustainable way. But everything here has really been about how do you mitigate additional space debris from happening, and how do you live in an environment that already has space debris. Fundamentally, I've already shown that we have certain orbits that are unstable. So we need to make sure that we actually remove some of the space debris. And there's been a few ideas that have been thrown around. On the is that working? Yeah, okay. On the top right here, you there's an idea of you can send a satellite into space and go and collect some object, catch it safely. This reminds me of like the claw games that you play at like the arcade to find some really cool thing, but instead you're catching whatever space trash that you have. This is from Clear Space One. It's a ESA, the European Space Agency mission, expected to launch in 2029. So there's this, and there's a few other ideas out there, but the basic idea is take a satellite, go grab some piece of space trash up there, and either bring it back down safely or just move that space trash into an orbit that we know is going to decay safely. There's another option called the laser orbital debris removal, or as a much more fun name is the laser broom, where it's basically you take a really high power laser, whether you're space based or ground based, and you shoot at it with their known orbital trajectories of these space objects, and you ablate a part of that into a plasma. So part of the object becomes a plasma. It changes its momentum ever so slightly and causes just enough little tiny kicks, just like little tiny little kicks, to make it so that it makes its way into an orbital decay pattern to make its way back down to Earth. So these are some ideas that people have thought of to actively remove objects, but there hasn't really been very much of an economic incentive to do so because, like all pollution, space debris is a negative economic externality. What that means is that if I want to shoot an object into space and I say I don't care about space debris, that's okay because I'm not actively being penalized for that, so I'm never going to see really the ramifications of my actions. And I can always pass that buck along to someone else. And this is usually the collective us of society. We are the ones that are going to be dealing with this problem. This is sometimes also called the tragedy of the commons. So because of this, and as I said before, the IADC is not a regulatory body, right? There's no penalty. No one's actually seeing a penalty that will cause them to change their behavior to make sure they work in a more sustainable way for space. And this is why all pollution, trash, climate change, all the different types of pollution that we have are so difficult for us to grapple with, is because these are all negative economic externalities. We can always keep passing that buck along to someone else, to someone else, to someone else, until eventually, sure, we'll have to deal with it. But at that point, I think it's already too late, right? So what I do want to point out is that there have been some aspects that have worked out really well. On the right here, I have a plot of the share of compliant objects. The top line is rocket bodies, and over time, rocket bodies have actually become very compliant. We're now at about 80%, I think. That a rocket is only allowed to stay so many years in an orbit before it needs to make its way back down to Earth safely, and we've been doing a really good job of that. And I think part of that is probably due to the Falcon 9, and its success in being able to bring a bunch of the rocket stuff back down to Earth safely. So that's great. But the payloads, which is the bottom line, is not so much. That's been kind of switching between 10 to 20%. So there's still a lot of work that needs to be done there. And although all the initial objects were primarily there due to government entities and they have their fair share of blame on the objects that have been made, modern day space infrastructure is becoming increasingly dominated by private industry. So there's something that we really need to make sure that there's some sort of regulatory body or something that we do to make sure that they will become good stewards of our near Earth space environment when they're the ones that are going to, in some sense, be controlling large aspects of it. So the next part, I want to kind of move towards the actual research that I do and some of my colleagues that are directly near to me and more of my peers in the community do, is more on the lines of space debris detection. So to remove the objects, first we have to find them. We can't get rid of them with our big satellite to bring it up there if we don't know where it is first. And some of the bigger pieces, it's great. It's kind of very clear we know where they are. But it's the smaller pieces that we really need to worry about and kind of have a better understanding of. So these are just a few of the ways that we can measure them. One method is through optical measurements. So as an example, this is the Cerro Tololo Inter-American Observatory in Chile. Basically, there's the sun's light hits a debris object or a satellite or whatever it is. It bounces back. Some of that light makes its way to Earth, goes into the satellite, and we can make a measurement of the debris particle that way. We can also use radar measurements. On the bottom here, the Goldstone radar in California. Radars transmit radio waves, which is an electromagnetic wave. It'll hit some of that, some of those objects, and some of that will return back to the radar, and they can have some really fine resolution, and they can capture some really small sized particles. So this is all really, really great stuff. Another way that we can do it, it won't give us like, we know this particle is over here at this trajectory, but this is a way that we can obtain kind of the general statistics of what might actually be out there, is when we look at the craters on satellite parts that have safely returned to the planet, we can examine them and then get a size distribution or a orbit distribution by just looking at the craters of these satellite parts. So that's another interesting thing that we can get. But what we're hoping to do is we're hoping to find another method to be able to detect small objects that are under about 1 centimeter in size. So I want to use this analogy, and I want us to remember that space is not a vacuum, right? So we have some object in space moving along, very much like a boat that we have over here. A boat's moving along the water. It's generating a wake, right? If we were on the beach in the distance and we saw this boat, we'd be like, I see a boat, I see a wake, I hear a boat, right? Those are all things that we can do to detect this boat. And that's what we want to do to see if we can measure not just some hard scatter off the boat. Can we measure something about this wake, which is bigger and longer lasting than the boat? And then maybe that's something that we can use to measure some of these smaller debris particles. And space is not a vacuum, yes, but I also did not tell you about a particular thing that does exist in space. Is the previous slides I showed were all about neutral particles, but we actually have charged particles that exist in space as well, in the upper atmosphere or the ionosphere, which is where I do a lot of my research in. And these charged particles, or ionized gas, is typically called a plasma, which I think most people know as the fourth state of matter. And that's the work that I do. I'm a plasma physicist. So the ionosphere, we've got this plot over here. So the blue line here is the neutral particles. That's the same exact line I showed earlier. This other line here is the plasma. And you can see there's less of it, but there's enough of it that we can get a lot of interesting information out of it. And we can see that there's kind of 3 different regions, the D, the E, and the F, and they all behave in slightly different ways. But the key thing that we're going to be able to use from this is that how can we understand how the wake of a debris particle behaves when now it's going through a bunch of plasma, and plasma is charged, so will interact with electromagnetic waves. And the beauty of this is that electromagnetic plasmas have so many more waves than neutral particles. Neutral particles are kind of limited in the amount of waves that they have. Plasmas, I have this crazy looking diagram here that I don't expect anyone to understand because sometimes I even have a hard time understanding it. It's called a CMA diagram. I believe it's named for some of the people that worked on it. But the basic idea is your y-axis is your magnetic field, your x-axis is your density. Now, depending on where your plasma density is and what your background magnetic field is going to determine where you live in this plot. And then depending on the direction of where you're looking at, you're going to look either perpendicular to the field, at a slight angle to the field, and there's going to be all these sorts of different waves, upper hybrid waves, lower hybrid waves, X modes, O modes, R modes, all sorts of different things, resonances. These are all things that we have really great physical understandings of, and these are all things that can interact with electromagnetic waves, such as radio waves, that we might be able to use to better understand the plasma and better understand the wake. So this is really the crux of what it is that we're looking at, is how can we understand some of this, complicated physics picture to back out, there's a debris particle over there, and I know its orbit. So what we have here is, this is some really great work done by Matthew Idzo at University of Washington, and he had a publication on it recently in 2024. I'm going to be showing a video in a second of a simulation, but basically we have a metal boat going through an ocean of plasma. And this metal boat is, metal is a conductor of electricity, becomes charged. So what you end up having is a charged object going through a plasma, and it launches these lower hybrid waves. So what we see is over time, you see the object moving to the right, and you see this wave structure kind of tailing behind it. And this structure is a bit bigger than the object. So maybe this is something that is actually measurable, right? So a lot of this is initial work that we're doing to understand the physics of what's going on with the actual wake structure, because once we understand that, then we can go in and try to do actual measurements to understand if we can get something useful out of this. I'm pointing out here, there's a circle on the top right with a dot in it and then a B. That's a notation to tell us that there's a magnetic field coming out of the page. And this is going to be useful for the next few slides. So this is one set of work. This is, as I said, this is cutting edge research. So there's a lot of interesting stuff going on right now. This is a different paper from Eliasson and Bernhardt, recently published in 2025. And the idea of this paper is, imagine we were looking at it in a plane like this. Now we're going to be looking at a cross section in this way instead. So we have, think of this as up-down. So a satellite is moving in this direction, and it's creating a wake of the same sort of wake that we saw in the previous simulation. That's these wave structures that we see here, these lower hybrid waves. Now, sometimes, I missed one important point. What's useful about this is that it increased the footprint of this particular satellite or object or whatever from 25 centimeters to a meter. So that might be big enough to be like, maybe that's measurable. But one very common thing that occurs in the ionosphere is you get these density striations. On the bottom plot here, we have striation density. We see like there's a little dip in the density. See this line over here? This is a little bit less density than the areas around it. So what happens is the satellite exists here. It launches a lower hybrid wave going this way. That lower hybrid wave interacts with this dip in the density. Note in this case, our magnetic field is pointed upwards. It interacts with this dip in the density, and that lower hybrid wave turns into waves that we call Whistler waves. Whistler waves are named because way back when we were learning about plasmas and radios, we kept hearing this whistling sound, and they were like, "What is this?" "Oh, it's this wave that keeps showing up. Let's call it a whistler." So we can see that this wave ends up propagating. If I can find it, it ends up propagating once it's a density striation up and down the magnetic field line. For this plot is showing between plus minus 5 kilometers. So maybe this is another method that we can use to detect space debris, is if we see that there's like these density striations nearby, whether they're happening naturally or whether we can induce them. There are facilities that we have that we could induce these sorts of variations in the ionospheric density. Maybe we can cause these other types of waves to develop that propagate a little bit further away. But one key thing that we need to be careful about with all of these things is we need to make sure that the waves that we're seeing are actually visible and not lost in the natural plasma. So to go back to my boat analogy, imagine I'm standing on the beach. The boat is some distance away from me, pretty far. Boat goes by. It makes the wake. That wake of the boat eventually is going to make its way towards me at the beach, right? But the beach has been wavy all day, right? How am I going to know that this is the wave of the boat versus just the natural wave of the beach that it was going to do anyway? So the way to do that is we need to keep doing a bit more work to understand what's actually going on with these plasma waves to make sure we can truly differentiate between what's this artificial source of plasma, this source of plasma wave, and a natural source that might already just exist in the ionosphere. And if we zoom in a little bit more, this is another work from Ganguly et al. 2025. We zoom in to capture what we call the kinetic physics, which is looking at like each individual particle and understanding its interaction with each other, whereas before we were looking at fluid models, which kind of looked at bulk properties, which is useful, but also they end up not capturing all of the physics of what's going on. But the problem with kinetic models is it's usually more computationally expensive and more difficult to run. So you usually have to make some sort of trade-off computationally for, do I want an answer today, or do I want to wait 10 years to get an answer that's more correct? So sometimes you go with the answer today. But because of these set of plots are actually moving at a slightly slower speed, because I think computationally they didn't have the ability to run it at a higher speed. But the interesting thing about this plot, this work here, is these two sets of simulations have the magnetic field either pointed towards the right, which is exactly in the direction of the satellite motion, or at a slight angle away, but still with some component in the direction of the satellite motion. And what they've wonderfully done is the object started towards the left and it propagated towards the right. But in this plot, they have defined their zero right here is exactly where the satellite is. And what's really interesting about this is, one, that the wave structure is different than the previous case, but also there are waves ahead of the satellite, whereas we didn't see that before. And these waves are called solitons. These are ion acoustic solitons caused by the ion sound speed. And solitons are nonlinear self-reinforcing wave packets, and they're strongly stable. So these are things that actually will stick around for a while, whereas a lot of these other waves do eventually decay over time and space. So this is actually something that maybe is a measurable thing that we can see that sticks around for a while, that might have a pattern that we could get at. But there's still a lot more that we need to learn. The other interesting thing is that these waves, these solitons, seem to follow the magnetic field. Right? On the plots towards the right, we can see that they're moving at an angle, even though the satellite is moving directly to the right over here. And this other last interesting bit that I don't know how much any of us truly understand yet is, we see in this case here, with a field out of the plane, similar to the first set of simulations I showed, you see that they've got these vortical structures. So maybe that's something that we can use to get a better understanding. But this is kind of really super novel research that we're trying to get an understanding of how to do all this. So how do we measure this? We can measure this plasma wake using incoherent scatter radars, or ISRs. So by the time they propagate to the ground, they'll likely have decayed a bunch. But what if we launched a radio wave at it? So ISRs, or incoherent scatter radars, I've got some examples here from our Millstone Hill ISR and our Poker Flat ISR in Alaska. And the basic idea of that is it's through a physics process called Thomson scattering, where you shoot an electromagnetic wave, in this case a radio wave. It hits a charged particle. That charged particle gets pushed a little bit because it was an electromagnetic wave that hit it. As that charged particle gets pushed, it releases another photon of some other frequency of electromagnetic wave. And some number of those photons will come back to our receiver, and we'll get some really interesting pattern. It's going to look like this pattern we have on the bottom left. And the pattern, we see really strong peaks at resonances that are frequencies that are very important for a plasma. The middle line here, which is, I have the middle line, and then I zoom in to the middle line because it's just so much bigger than the rest, is called the ion line. This is based on the ion acoustic mode, or the ion sound speed. Then we have the gyro line, which is based on the frequency at which electrons gyrate about a magnetic field. And then we have the plasma line, which is based on kind of a fundamental frequency of a plasma. It's a very natural frequency of a plasma. So we can use these sorts of spectra in our understanding of plasma waves to back out actual plasma parameters from this. So this is a typical ion line spectrum, and you can see that the width of the spectrum is related to the ion acoustic frequency, which is a function of your ion electron temperatures and your mass. The ratio of the dip to the peak is related to the ratio of your temperatures, and the total area can be used to estimate your density. So these are ways in which we can back out some nice plasma parameters from an incoherent scatter radar. But the problem is, these assume a nice equilibrium plasma from linear theory, and all those simulations I showed you were very, very far from equilibrium and very, very, very highly nonlinear. So how are we going to continue doing this? One example is Dr. William Longley from who's my colleague in my research group, has done some really interesting work and finding that we can have these waves interact very nonlinearly with the ion acoustic wave, or the ion acoustic mode. So in some regions of the ionosphere, you can have this photoelectron distribution where you have the sun's light comes in, ionizes a particular particle, and makes a large population of energetic electrons that exist in the ionosphere. Those energetic electrons drive what's called an upper hybrid mode unstable. That part doesn't really matter so much. But the key thing to note is that we have an instability region occurring in this part that needs to map down to an observed region over here. We could think of this plot here on the bottom left as a plot of our wavelength of our wave and our frequency of our wave. And depending on our radar, we're only going to capture some little part of this plot over here. And that part on the bottom left is the part that we can measure, at least at this facility over here, whatever facility that they're talking about. So what he did was he did some really interesting work to show that if you do this sort of coupling, you see that there's the dashed line is with the nonlinear theory, and the solid line is with the linear theory. And you can see if we don't take it into account and we look at the actual data, we're going to have huge errors and we're not going to truly understand what's going on. So we're hoping to use some of the work like this in an effort to kind of map down some of these other really interesting waves I showed in the previous slides to the ion acoustic mode, which is the most measurable mode. There's just the most power that we could get back from our radars for that mode. And in a recent paper that I developed an improved method to do a lot of these nonlinear calculations. I didn't talk about my work because it's all math and I think everyone would get bored. So what's left to do? I mean, a lot. We're really only at the very beginning of this research, so there's a long way to go. So we got to do a lot of this theory work to understand that wave mode coupling. And then once we understand that, the question is, can we even find a distinct signature that we could search for? Like, we don't know if this is even truly a feasibility yet, so we're really testing the waters and to see if this will work. So, but supposing we can find a distinct signature that's different from something natural that we could look at, maybe then we can test it on a known debris particle or a known satellite. You know, if we already know what the answer is and we can kind of back out that correct answer, then maybe we'll be able to have some sort of confidence. And as it continues to orbit based on Kepler's laws, the periodicity, each successive orbit will improve our confidence. And then eventually we'll be able to make projections on future trajectories and start using it to actually measure debris, which will be absolutely fascinating. And we're hoping, that's, sooner rather than later, but this is still, the first few steps of a very complicated physics problem that we're trying to tackle. So in conclusion, I guess the main point of my talk is that we need to become better stewards of our space environment. We've left all these objects in space that have been colliding with each other, and they're just going to keep making more objects. And we've made these guidelines that include end-of-life care and really strong engineering considerations to make sure that we can keep everything nice and safe. We need to make sure that those guidelines are kept and followed, and we need to have some sort of regulatory body to do that. And scientists like myself and many other people are working on methods to better monitor and then hopefully remove a lot of this space debris. I've got here just an example plot of showing, 1957, this was our planet. Sputnik was the only thing around it at the time, just for a few months. 92, we see that there's more. Now 2015, we see that there's more, and that was still 10 years ago. So there's even more stuff now. That's in the other plot I showed you. So I want to leave you with this last statement that I've written here is, let us hope to continue having science funding that will allow us to foster our near-Earth space environment so that the future generations will be able to benefit from all the really cool stuff that we've been able to do so far. Thank you very much for your time. Are there any questions?
All right. Thank you for an excellent presentation. So we are going to do a question and answer session because I'm sure people have questions out here as well as our online chat. Just a brief overview of the safety briefing, though. If you need to use the restroom, that is the porta potty in back. It is blue when you have color vision, that when you're not staring at it at night. It is illuminated by red for ease of finding it. After the presentation, I will be manning the museum and gift shop area. Unfortunately, they still don't allow me to break the laws of physics and be in two places at once. So I will be in there after the question and answer session. When we are walking around, because it is quite dark, do try and keep those flashlights and other lights you might be using to wander around pointed towards the ground so we don't accidentally blind people. That being said, we are using our headlights because we don't want to get run over. So, for question and answer, how it's going to work for the people here, you're going to raise your hand and wave it about, and keep it up and kind of wave it occasionally, because I am like the Jurassic Park T-Rex, and if you put your hand down, I lose you in the darkness because I have no night vision since I've been staring at online chat. Online chat, you have a DC, you just get to type your question. I'm going to bring the people here the microphone so that other people can also hear your question. But I'm going to start this off with our first online question, which was, what is the weirdest piece of space trash you know of?
Weirdest piece of space trash I know of.
I was going to say
there's
the
probably
Roadster, the Tesla Roadster.
I guess there's that one. That's definitely a weird one. One funny thing. There's probably a lot of human poop up there from like International Space Station. I don't know where they'd send it afterwards.
I don't know, but that would really be. There's a joke I can make, but unfortunately it's a bit above PG-13, so I can't make it. If you are taken out by a flying piece of poop, that's obviously a fill-in-the-blank situation. All the adults will get the joke. Right, we have a question over here, and he followed directions, except for the fact he put his hand down, but I still...
Hello. I want to ask, like, where's the bathroom? I want to.
That is the porta potty in the back. It is right there.
Oh, my bad. I'm sorry.
It's fitting. I was the one that brought up the poop. Okay, there's a question over there.
It's self-fulfilling prophecy.
It's like all the objects in orbit, like they have some ability for thrust, except like the dead ones and
Right.
all these like small objects. Couldn't you create like a friction in the space and plasma, and then that would throw off the velocities of the orbiting particles, and maybe they'd fall out of orbit or decay like that?
Yeah, there's multiple ways to do that. You can't do it like as a whole because there's just so much surface area, there's so much stuff. But there's like that laser broom idea kind of is in a way doing that for like individual particles. One thing is that actually kind of happens naturally. Actually happened recently. I think there's a few. You might have seen articles showing that a few Starlink satellites have re-entered faster than we thought they would, and that's because we're now in a period of solar maximum. So there's more influx of particles coming from the sun, and that actually adds to the drag that some of the objects see. And that causes an increase in our atmosphere too, an expansion of our atmosphere. So to answer your question is, we could do it on small scales, but we can't do it on like, let's clear an entire orbit by doing that, just because the amount of energy required to do that is so insanely large. Like, we are but a tiny little ape on a big rock, you know?
All right, we have another question over here.
So when you think on the Earth, we can think on, okay, if we make the particles smaller, we can collect them, quote unquote, easier.
Mm-hmm.
But the problem here is it doesn't matter if we make it smaller because they continue being as dangerous as you show,
Yeah.
one. But second, even if that will be, plausible, how'd you collect them and get rid of them? Because that's the as I was listening to you, what I was thinking is, okay, but there is impossible to collect and
Yeah, that's a huge area of active research. I don't know all the answers to that because I'm mainly doing like the detection side. But there's ideas out there of like making like big nets to capture some of the smaller pieces of debris particles. But I think the smaller ones, they're bad. But I think the real issues for a lot of the cases are like the bigger ones, because they cause like really catastrophic crashes. But like the really small ones, I think, are things that we need to just try to make sure that we we mitigate and figure out ways to just make sure that they slowly decay in orbit as opposed to just sitting around forever. But yeah, no, I don't have an answer for you because that's a very hard question, but it's a very poignant question because the big objects, like that big claw will grab a big object, no problem, but it's not going to grab, all those little chips of paint that are moving around. Yeah.
Right. Online people, I do suggest if you do have questions, do get them in. And one of our online viewers added that apparently Gene Roddenberry's ashes are up there. So the creator of Star Trek.
Oh, that's nice.
So, yay, dead people in space. Right, we got a question over here.
So you spoke a little bit about the rate of decay of these objects that are circulating in space, and if you think about it in terms of on Earth, plastic we know has a very long lead time to actually decay. Are there specific materials that have longer lead time that are more of a focus area than other materials?
That's a great question. It's not really dependent on the material per se. The decay time doesn't have anything to do with like the object slowly breaks down and becomes smaller and smaller little pieces. The decay time has to do with how big the object is and how much of a surface area of other stuff that it's hitting. So the bigger the object is, in terms of like surface area, like front-facing surface area, the more particles it'll hit, and the more its trajectory will get slowed down a little. So it has less to do with the material and more to do with its size relative to everything else. I'm sure to some extent maybe materials might play a role in like once it does re-enter, if it's made of a really strong material, maybe it'll survive enough to actually hit the Earth. But if it's a really weak material, then maybe it'll just disintegrate it and it won't really actually make any sort of impact on the planet.
All right. Our next online question is, and I think you answered this during your presentation. Do companies and governments have a rule, like, of a maximum amount of stuff we can put into Earth orbits before it becomes a hazard, not only for more things launching, but also life on the planet? Like, here is the maximum amount of objects.
I don't think we have a number of maximum amount of objects. I think it's also from the perspective of we all know that we're going to keep increasing the number of objects. Based on the plots that I showed, we're already in some orbits already unstable. So if we consider that as our maximum number of objects, we've already passed it. The true answer should be we have the number of objects that we need, and then we take away the things that we don't. That's hard to do.
Right, we got another question out here.
You mentioned that the Sputnik was orbiting around the Earth for a couple of months, and then it went down. So I'm wondering what is the average decay time for like smaller and larger objects. And I also heard that International Space Station needed to be boosted with speed and altitude every couple of months as well.
Yes.
So is the decay time in couple of months or couple of years or hundreds of years?
Yeah.
That's my question.
Let's go back to this slide over here. Okay. Yeah. So this slide here has the decay times. They do change a little bit as a function of space, like a function of like how big the object is. But this is kind of the general, guideline. So I don't know. I think the International Space Station is like 100 something. I don't know. I don't remember what.
I also think it's a function of speed.
It's a function of
because if you're going fast enough, you can.
Yeah.
Keep going longer.
Yeah. Yeah. The so built into altitude is also a speed. So the lower you are in altitude, the higher your speed has to be, just by nature of the way gravity works. But yeah, so I don't know off the top of my head what the orbit of the International Space Station is, but this is kind of the estimated decay time. So if nothing really operates at 100 kilometers because you're going to be gone in 2 hours. But anything more than that, you definitely need to have consistent amount of thrust to push you back into the proper orbit. Yeah, and this is just a very simplified calculation. You can get much more good estimates once you know like what is the actual orbit that you care about. Some orbits are like you're really close to the Earth on one side, but then you're really far on the other side for whatever mission that you're trying to do. So when you're close to the Earth, that's when you lose all of your momentum. But when you're far from the Earth, you don't lose much of your momentum. So you have to. It's a game of trying to figure out
gravity slingshot assist
gravity
sort of
slingshot
thing.
assists. But it's also you need to take into account. There's a lot that goes into like the actual engineering of a space mission, because you need to take into account, okay, if I'm in a particular orbit and I need to know I need to do all this thrust, well, I've now added mass to my spacecraft because I have to have propellant to thrust me for this much period of time. So then you need to, it's like this constant revision cycle that you need to keep doing to make sure you get your final mission doing whatever you need it to do.
All right. Last call for any questions out here, because it looks like our online questions are also done. All right. So I do want to thank everyone who has come out here and has joined us online. I do hope everyone enjoys this nice, clear night. It's been a rough season. We haven't gotten a lot of those, but we do have a number of telescopes open. Each of the sheds that has a roll-off roof has its telescope if the roof is rolled off. There's a volunteer running that scope. In addition, I do know we have a number of our volunteers have their own personal telescope rigs, so do feel free to ask people what they are looking at through those telescopes. With that, I do want to wish everyone a great night, clear skies, and good